Come back to explained. We love to take those topics that are maybe a little bit tricky and make them crystal clear for everyone. And today is no exception. We're going to be diving into data structures, specifically dictionaries.
Yeah.
But before you go and grab those big old dusty books off the shelf, we're not exactly talking about those kinds of dictionaries.
That's right. Dictionaries in computer science, they're a little limited. They're not really about words and their definitions. They're more about how computers store information and then can find it really, really quickly.
Yeah, so it's less about like vocabulary and more about efficiency.
Exactly. Think of it this way. If you want to look up a word in a real dictionary, how do you find it so fast? It's because all the words are organized alphabetically, right? You can just flip right to the section you need. Well, dictionaries in programming, they work in a similar way. They let us store information so that we can retrieve it super efficiently using a key, just like you use a word to find its meaning.
Okay, I think I'm starting to see the connection here. But before we get too deep into the how, let's just think about how we see this in our everyday digital lives, right? I mean, have you ever thought about how your phone can predict the next word you're going to type? Or how a search engine can go through billions of web pages in just a fraction of a second? It's mind-blowing. Drop your guesses down in the comments. We'd love to hear what you think.
You're exactly right. Dictionaries are the engine behind so much of the cool stuff we see in tech these days. And what's even cooler is that there are a bunch of different kinds of dictionaries, each with its own strengths and weaknesses. It's like choosing the right tool for the job. And in this deep dive, we're going to be exploring these different types, from simple arrays to more complex structures like linked lists.
Okay, I am ready to get organized.
Yeah.
But before we jump into all the different types, can we just step back and clarify one thing? What exactly is the difference between a container and a dictionary? I mean, they both involve storing data.
Right. Yeah, you're right. Both containers and dictionaries deal with storing data, but the real difference is how they access that data. Remember those containers we talked about a while back? They're basically just a way to hold a bunch of data together, like a box filled with random stuff. There's stuff in there, but there's no easy way to find a specific item.
So it's like when I'm trying to find my keys in my overflowing bag.
Uh-huh, exactly. Now, a dictionary is like a super organized version of that box. Instead of just storing the data, it gives you a way to find any item instantly using its unique label or its key. So instead of rummaging through your bag, you can just say, "Get me the item with the keys label," and boom, you got it. That's the power of a dictionary. It acts like a lookup table connecting keys directly to their values.
I am loving this organized version way more. So it's all about having a system for retrieving information based on a specific key. Got it. Now, you mentioned directly addressable arrays as one type of dictionary. What makes them so special?
Directly addressable arrays are a really cool example of how efficient dictionaries can be in the right situations. Let's say you have a list of people's ages, and you want to count how many people are each age. The cool thing is the age itself can be the key, because we're dealing with ages which usually fall within a certain range. We can actually use the age value directly as the index in the array. The count for each age then becomes the value that's stored at that index.
So if I want to know how many people are 25, I would just look at the 25th spot in the array.
You got it. And it's this direct mapping that makes it so fast. In computer science terms, we call this O1 efficiency, which means it takes the same amount of time to find any age, no matter how long that list is.
Okay, that makes sense. I'm starting to see how this can really speed things up.
Yeah.
But what happens if you have duplicate keys, like two people who are both 25?
That's a great question. To handle those duplicates, instead of just storing a single value at each index, we can actually use something called a linked list. So each time we come across the same age, we just add it to the linked list at that specific index. We'll get into linked lists a little bit later. But for now, just remember that they're a handy way to manage these tricky situations.
Okay, so directly addressable arrays are super speedy when our keys can be used as an index. But what happens when that's not possible? Like if the keys are more complex?
Well, that's where things start to get even more interesting. Then we move into the realm of unordered arrays, where the keys don't have that neat and clean mapping to an index.
So it's kind of like having a jumbled box of stuff again, but this time with no labels at all?
Exactly. Searching in an unordered array is a lot like digging through that messy box. You got to check each item one by one until you find what you're looking for. This is what we call a linear search. And it can be pretty inefficient, especially when the array starts to get really big.
So finding something in an unordered array can be a real pain. But what about adding or removing things from it? Is that any easier?
Actually, yeah. Adding and removing elements from an unordered array is super simple. Since we don't really care about keeping things in a specific order, we can just stick new elements onto the end or replace an element we remove with the last one in the array. Both of these operations happen in constant time, or O1, which means they're very efficient.
Interesting. So unordered arrays are good for adding and removing things quickly, but not so much for searching. Is there any way to make the searching part faster?
There are definitely a few tricks we can use to optimize things. One common way is to keep track of how often each element is accessed, and then rearrange the array so that the most popular items are all at the beginning.
So kind of like organizing my messy box, so the things I use most are always within reach.
Exactly. With a bit of organization, even unordered arrays can be pretty efficient. So we've got unordered arrays, but what about when we need our data to be in order? Don't forget to follow Explained for even more deep dives into all sorts of cool topics. That brings us to ordered arrays. Now, in ordered arrays, all of the elements are arranged based on their keys, which opens up a whole new world of search techniques like binary search.
Binary search, I think I've heard of that. It's like looking for a word in a dictionary. You just keep splitting the dictionary in half until you find the right page.
Exactly. That's a perfect analogy. With binary search, we compare the key we're looking for with the middle element in the array. If our key is smaller than the middle one, we know to look in the first half of the array, and if it's bigger, we know it's got to be in the second half. We just keep repeating this process, cutting the search area in half each time until we find what we're looking for.
It's a classic divide and conquer strategy. This definitely sounds way faster than going through each element one by one.
It is. Binary search has what we call logarithmic time complexity, or OLGN. This means the time it takes to search grows much more slowly than with a linear search. Like in a sorted array of 1,000 elements, a binary search can find any element in at most 10 steps, whereas a linear search could take up to 1,000 steps.
Wow, that's a huge difference. Ordered arrays seem like the clear winner when it comes to searching speed. But I'm guessing there's got to be a downside, right? There's always a trade-off.
You're right. While searching is super fast in an ordered array, adding and removing elements can be a bit trickier.
I guess it makes sense. It's kind of like trying to add a new word to a physical dictionary. You'd have to shift all the words that come after it to make room.
Exactly. Adding or removing an element in an ordered array means we first got to find the right spot for it, which takes OLGN time using binary search. But then we have to shift all the following elements to make space or to close the gap, which could take ON time in a worst-case scenario.
Okay, so it's a bit of a balancing act. Ordered arrays are awesome for searching, but not ideal if you need to add or remove things a lot. What about when you need a data structure that can handle both of those things efficiently?
Well, that's where linked lists come in. They offer a completely different way to organize data, and they're super flexible.
Linked lists. Okay, so how do those work?
So imagine a linked list like a chain where each link is a piece of data, and each link not only holds the data itself, but it also has a pointer to the next link in the chain.
So instead of storing everything in a row like an array, a linked list connects the data using these pointers. That sounds pretty flexible.
It is. This structure gives us a lot of flexibility. We can have unordered linked lists where we just add data in any order. We can have linked lists that are ordered by frequency of access, kind of like those optimized unordered arrays we talked about. Or we can have strictly ordered linked lists where everything's arranged based on the keys.
Okay, cool. So how does this structure affect the speed of things like searching, adding, and removing data?
Well, adding and removing elements in a linked list is super easy. All we have to do is tweak those pointers to either insert a new link or remove an existing one. And these operations take constant time, which we represent as O1, so they're really fast.
Wow, that's even faster than unordered arrays.
Yeah.
But what about searching? Do we still have to go through the entire chain one by one?
Unfortunately, searching in a basic linked list is still a linear process, ON time. We have to start at the beginning and follow those pointers until we find what we're looking for.
Okay, so that's a trade-off. Again, super fast for adding and removing things, but potentially slower for searching. Is there any way to make the searching faster in linked lists?
Absolutely. There's a really cool variation called a skip list. It's like a linked list, but with multiple levels of links, which allows us to skip over big chunks of the chain when we're searching.
Skip lists sound pretty advanced. Maybe we can explore that in another episode. But for now, I think we've covered a lot about dictionaries. We talked about directly addressable arrays, unordered arrays, ordered arrays, and even touched on linked lists.
Yeah, we did. And remember, there's no one best type of dictionary. The choice depends entirely on what you need to do with your data. If you need really fast lookups and you can use your keys directly as indices, then directly addressable arrays are the way to go. If speed for adding and removing elements is more important and the order doesn't matter, then go with unordered arrays. If you need to search quickly in a dataset that doesn't change very often, then ordered arrays are great. And if you need a good balance of efficiency and flexibility, linked lists are a solid choice.
It's all about using the right tool for the job. So thinking about that, think about your favorite apps and websites. What kind of dictionaries do you think they use? Let us know in the comments.
You got it. Choosing the right data structure is really important for building software that runs smoothly and efficiently. And as you learn more about computer science, you'll discover even more sophisticated and powerful data structures.
Ooh, like what? Give us a sneak peek.
Well, there are hash tables, which use a special function to map keys to indices, making lookups super fast. And there are also binary trees, which organize data in a hierarchy for efficient searching, insertion, and deletion.
Hash tables and binary trees. Sounds like a whole other deep dive waiting to happen.
They definitely are. Those are kind of the next level of data structures, each with their own special properties and uses. Understanding them opens up a whole new world of possibilities.
Okay, you've officially piqued my interest. We'll have to cover those in a future episode. But for now, I think we've done a pretty good job of explaining the basics of dictionaries and how they help us organize and access data.
I agree. Dictionaries are kind of the unsung heroes of computer science. They're behind so much from simple stuff like spell checking to complex stuff like databases and even AI. So understanding how they work is really important for anyone who wants to understand how software and algorithms really work.
Yeah, it's amazing to see how these simple concepts like arrays and linked lists can be used to create such powerful tools. It really shows you how much ingenuity and creativity goes into computer science.
Definitely. And as we keep exploring the world of data structures, we're going to see even more amazing examples of that.
So if you're interested in learning more about these data structures like hash tables and binary trees, be sure to follow Explained. We'll be diving into those topics in future episodes, so hit that follow button so you don't miss out.
And if there are any other topics you'd like us to explain, leave us a comment below. We're always looking for new ideas for deep dives.
That's right. We love hearing from you. Your suggestions help us shape the show, so please keep those comments coming.
Okay. So with that, I think it's time to wrap up this deep dive into the world of dictionaries.
It's been an awesome journey exploring how these fundamental data structures work. From simple arrays to linked lists and beyond, we've seen how each type has its pros and cons, making them suitable for different tasks.
And the main takeaway is that understanding these data structures and their trade-off is key to designing good algorithms and building powerful applications.
Absolutely. So thank you for joining us on this episode of Explained. We hope you learned a lot about dictionaries and how they impact the digital world.
Until next time, keep exploring, keep learning, and keep those brains buzzing.
It really is amazing how these basic building blocks of computer science can be so powerful. And we've only just scratched the surface.
Yeah, for sure. The world of data structures is huge, and it's always changing. But even just knowing these basic concepts about dictionaries, you can start to see how computers handle information so efficiently.
All right, so before we wrap up, I have a little challenge for you guys listening. Think of a real-world situation where you need to store and retrieve information really quickly. What kind of dictionary would you use, and why? Let's hear those creative ideas down in the comments.
That's a great challenge. It's always cool to see how these ideas can be used to solve real problems.
And remember, if you want to learn more about all this stuff, like hash tables and binary trees or anything else about the digital world, be sure to follow Explained. We'll be back with more deep dives soon, so make sure you hit that follow button.
That's right. We're always here to break down those complex tech concepts and make them easy to understand.
So until next time, keep those brains buzzing and keep exploring the digital world. Thanks for joining us on Explained.